Welcome to HyperStudy Training. This class will be broken down into several modules, but before we get started, let's talk a little bit about why we might want to use HyperStudy, if it's a good fit for our applications, and a high-level overview of the general capabilities of HyperStudy. My name is Lacey, and I'm an application engineer at Altair. I'll be walking us through how to use HyperStudy. In this training course, we'll have several modules. The first module is going to be an introduction and how to set up HyperStudy. So right now you are in the introduction of why we want to use HyperStudy. The second module will talk about design of experiments. Module 3 will be about making fit models, and Module 4 will be about optimization. We say that HyperStudy is a design exploration tool, meaning that we take a look at a design and we want to learn more about it, to study and to analyze it further. And design exploration within HyperStudy is generally associated with a few different key terms. Some of them are computer aided, so a lot of times we're looking at computer aided models and trying to supplement them or further understand what's happening. It's automated. We don't want to have to set up all of these different runs by hand. There's a lot of linking in HyperStudy so that the best designs are automatically generated and run. It's mathematically based in order to help us understand our design space. What are the possible design options within the parameters and the bounds that we have? And this allows us to better understand our design problems, discover better solutions, and also get to those optimized solutions faster, allowing us to make better design decisions in the time that we have. Let's stop to think for a moment about all the design decisions that can go into just a single part. Starters, we have the dimensions. We have this whole radius. We have the length along this component. We have different fillet radius on here. We have different heights that this part can take on and all of the dimensions that this part can take on. And that's before we get to what materials this part can be made out of. And so many more decisions like, where do I place the welds? What kind of fastener type should I use? Does the surface finish affect the performance of this part? What operating frequencies am I going to be at? How is it connected to other parts? What temperatures is this going to be operating at? Do I have any composites that need to be modeled? What orientation should those be at? And how many of that orientation do I need? What manufacturing process should I use? Really, there is an infinite number of possible designs, but we don't have an infinite amount of time to design these parts. When we think about all of these potential designs, we call this the design space. All of the designs that our part can possibly take on. Of all these possible designs, how do we find the best solution? What we need is a guide, and HyperStudy is going to be this guide to our design space. We can use HyperStudy at a high level to do a lot of different things. We can help narrow down the choices. So maybe we go from all of these infinite number of choices to a small subset of those choices. We also want to fill design space smartly so we don't have to try all of these designs. Within our design space, let's strategically choose some of these designs to test out to greater enhance our understanding of the design without having to try every single combination that's possible. If we're keeping with our guide analogy, we also want a map of how we move through this design space. So I have a length along this component, but how does my final result that I care about, how does that change if I change that ever so slightly? And when we do these trade-off studies, we're usually not doing them by running the solver every time, whether that's Flux or FICO or OptiStruct or Radios. We don't necessarily have to run that every time to get these kind of answers. There are certainly more efficient ways that we can do these trade-off studies. We also want to improve performance and reliability. How do we make a part that's lighter or stiffer or in some other way better performing? Or in a lot of cases for us, maybe that just means that it costs you less to build. So in some way, we want to understand the design space and improve upon our existing design. When we think about design exploration, we probably think about this in the way that it is done traditionally, which is we run a single simulation, we look at the results, maybe we add it to a spreadsheet if we are really feeling motivated, maybe it's got some screenshots of the result. We plot all of these things and say, is this a satisfactory result? Does it meet all of my requirements? And if you're like most of us, the answer the first time around or the second or the third is no. So you have to go in and iterate through this process. It takes a long time, and at the end, you're tired. What we want to do instead, rather than manually iterating through all of these, is identify the key parameters that are really driving the design. So we're not continuing to manipulate things that don't really influence the result that we care about. So we want to identify those key parameters, find the best design as quickly as possible, maybe even check the reliability of this, and then build a predictive model so that I don't have to call Radios and wait 12 hours for a run in the future. I have a model that can give me instantaneous answers about how the decisions that I'm making will influence my outcome. Within HyperStudy, we can do a lot of different things. The first one is investigate relationships. How do my inputs correspond to the outputs and the responses that I'm tracking? And there are a lot of buzzwords around the kinds of things that HyperStudy does right now. And I think one of them that we can associate with this investigate relationships block is certainly data mining. If we have a lot of runs, how do I parse out what's important and what's influencing the responses? We can also build fit models and do trade-off studies. You may also hear this referred to as a meta model or a surrogate model, but essentially what we're doing is replacing maybe our physics-based solver or even our Excel spreadsheet with a machine learning model that will give us instantaneous feedback when we start to adjust our input parameters to tell us how this affects the output parameters. And with all machine learning models, we don't just want to blindly trust that we are able to accurately capture that. So we're also going to get metrics that tell us about the quality of those fit models. Of course, we always want to improve our design performance. We have built-in optimization where the user can have an objective function. I want to minimize my mass maybe. And then these are my constraints. I can't have a displacement above this amount. My stress in my part can't be above this amount. So what is the best possible design that I can get within the constraints that I'm working with? And then being able to assess design reliability. Given my manufacturing tolerances or given the kinds of loads and the distribution of the loads that are likely to happen, how likely is my part to fail? Some of the key differentiators of HyperStudy, as opposed to maybe other design exploration tools, are first and foremost the usability. We do a lot of guiding for the user so that there's not a lot of upfront time to learn a new interface. If you're using HyperWorks tools, there are a lot of seamless integrations where HyperStudy can automatically link to a solver or to a preprocessor. But of course, we keep our open framework. We're happy to pair HyperStudy with another solver, and there's a lot of tutorials in the help document to help you pair other solvers as well. We also have state-of-the-art methods for reliable and robust product design. So when we talk about DOE or optimization, we do make a concerted effort to put the recommended option for the kinds of problems you're solving as the default, but you as the user are welcome to veer from that and set up your own methods or define a different course for your design exploration. And there's a lot of good visualization already built into HyperStudy to allow you to efficiently make things like correlation matrices or a linear effects plot. And these are just automated outcomes that already come out of the box with HyperStudy. The key things that we want to do and the benefits of doing these design explorations are to improve our design performance and the quality of our product. reduce the time that we have to spend developing these products and the costs to do that, and increase productivity and the return on the energy we are putting in. We'll take a deeper dive into these different topics within the different modules, but I want to give a high-level overview of what each of these things does. That way we can refer back to it and have a good idea of what we want to accomplish as we start the module. The first module is going to be linking up our solver or our model to HyperStudy so that we can automate a lot of this work. So we will do a setup. Very similar to a setup is a basic approach where we can test the initial values as well as the bounds by performing some nominal runs or checking at the system bounds. This just allows us to make sure that the settings we've done, if we combine them at the same time, are compatible with each other and not going to cause problems. The next module will be about design of experiments, and we'll call this DOE. There are actually two types of DOE. One of them is where we try to understand how changes in input variables affect our output responses and get a global understanding of the design problem. Maybe we start with 20 variables initially and try to really understand the 5 or 10 that are going to influence our design so we don't spend a lot of time varying things that don't actually influence the outcome. The second kind of DOE is going to be to fill the design space so that we can make these fit studies, these mathematical or machine learning models that are going to replace our maybe physics-based solver that we started with. We'll be able to, once we build a good fit model, adjust our inputs and see how that affects the outputs without running, for instance, FICO, Flux, or those physics-based solvers. And the advantage here is that we can get results a lot faster and not have to run that very computationally expensive solver. The last thing we're going to talk about in this class is optimization. What is the best design with essentially what I have to work with? So different constraints when I change my input variables, what is the best outcome I could have? And this is an advanced topic that's outside the scope of this class, but we can also within HyperStudy do these stochastic models. Rather than saying my input and my input thickness is always 0.1, I start to account for the fact that I have certain tolerances when I manufacture things. Sometimes my thickness is 0.1, and sometimes it's 0.095, and sometimes it's 0.11. We start to look at this with a more realistic approach and consider the different values and the likelihood that our model is to take on these different values and how that affects our outcomes. I really like this as a map, so to speak, and a summary of, for each approach or thing that we're going to do, why we might want to do this, how we're going to do it, and what the output responses are that we care about. We'll focus on the why right now and get to the how later in the class. As I mentioned, for DOE, there are two different reasons why we might want to do this. The first is to understand relationships and patterns and identify those key parameters. The second is to fill the design space. When we fill that design space, we usually want to build a fit model on top of it to replace expensive simulation runs and do some trade-off studies. We perform optimization to find the best design for our problem formulation, and then we make stochastic models in order to find variations in the responses due to variation in the inputs and understand the solution reliability. We'll usually be working with this .hstudy file. This contains your models, your variables, your output responses, and your approaches. What's really nice about this is as you automate these different runs, there's a nice tree structure where you can go in and query and see individual runs. So I might do, 100 OptiStruct runs, and then I'm interested in 5 of them. So I can drill down to those specific runs, go look at the results contour, and it's all nicely organized in this tree structure because we're working in this HyperStudy file. There are some common use cases. We won't go through every single one, but I wanted to have this up here for your reference. We'll start with an easy one here where we have a radios or an OptiStruct model, and we want to do a size or shape optimization. So we want to change with shape optimization the outer bounds, usually with morphing, and with size optimization, pretty much any parameter that we can parameterize can be done with size optimization. So we'll talk about how we might want to change shell thickness in a model. And it will just tell you one of your HyperStudy options, which is make a HyperWorks model, make that direct link with HyperStudy. We'll talk about how to do that. And your model type that you're setting up is a HyperMesh model. Another option here is that you're using a commercial FEA solver, but it's not HyperWorks, but you can pre-process this in HyperMesh, you can post-process in HyperView. So solvers like ANSYS, Abacus, LS-DYNA, and you'd like to run this size optimization, for instance, on a cluster. Your model type will be a parameterized file. You will parameterize this in the HyperStudy editor, and you will register the solver script. We'll talk about how to do this as we go through the class. Keep in mind that you don't have to necessarily have an FEA or CAE application to use HyperStudy. We also have options for linking Python scripts and spreadsheets. And of course, you can connect all of this if you want a model that has a physics-based solver and you need some corresponding values from an Excel spreadsheet, and maybe you have a Python script where you need to post-process. We can link all of these different things within HyperStudy and automate that process. There are some additional study questions and scenarios here, so we can link up to a CSV file, Inspire Studio. And one thing that I want to call attention to is the ability to do different physical models and link them, including some kind of dependency. Maybe we want to study a certain rail and it needs to have crash performance that we have to validate in radios. And we also have to validate some kind of vibration or normal modes analysis in OptiStruct. And just for fun, we're going to throw in that it has to be transmissible for some kind of antenna, and we also need to put FICO in there. We can link the inputs and the outputs for all of these solvers so that we can really have a multi-physics model and optimization running through HyperStudy. If this is something that you're interested in, doing optimization with multi-physics capability, I'd certainly encourage you to check out this paper. It can be found on our website or through your account manager, where we talk about multidisciplinary design optimization of a composite aircraft radome. In this example, there's a lot of different competing factors where we need to optimize the front component of this aircraft, but there's an antenna in there, so we have to be able to transmit. If a bird hits the outside of the airplane, we have to be able to handle that damage. And the front of our aircraft can't be this square box. We also need to have good aerodynamics that go into this plane. Like I said, if this is something that you're interested in looking at, please check it out, and it's definitely possible, and this was done actually with HyperStudy. If your questions are more general, instead of I have this solver, what model should I use? If you say, I have some input variables and I want to understand how they affect my output responses, well, let's point you to a design of experiments and suggest what method to use. These are the plots you should look at. What if I want to do trade-off studies? What if I want to minimize some objective and I have other design requirements? And then what if I want to look at the reliability of my design? So if you have these very high-level questions, please check out these slides for some guidance on which approach might fit the question or scenario you want to answer. Or of course, if you still don't know the answer, feel free to reach out. We're happy to provide some assistance in this area for people to get started. Hopefully this gives you a good idea of why we want to use HyperStudy and the kinds of applications we can use it for. Now we'll take a closer look at each of these modules to understand design of experiments, fit models, and optimization.